Greetings, dear colleagues. My name is Kirill Sahorsky, and today I will be presenting a paper titled Intelligent Landmine Detection with Unmanned Aerial Vehicle Mounted Thermal Camera by Siniglazov Viktor and Sahorsky Kirill. Let's briefly touch upon why mine pollution problem is so important. The problem of mine pollution is acute in a wide range of countries, including Ukraine, resulting in thousands of casualties every year. Although some types of mines can be detected by using remote sensors minimizing the hazard, humanitarian landmine clearing is still largely a manual process. Assuming the current rate of detection and clearance of landmines remains the same level of 100,000 units annually, it is estimated that 500 years is required to clear all existing explosive ordnance, not including landmines yet to be installed. Lack of funds for mine detection and removal leads to a limited use of explosive ordnance detection and clearance technologies, which further slows down the progress. There are two primary challenges to landmine detection in the modern age. First one being plastic mines. Modern explosive ordnance, especially landmines, utilize more plastic components rather than metal, leading to existing methods of identification being unreliable. Then there is debris pollution. Minefields are likely to contain metal chaff and other debris introduced either as a result of combat or intentionally during the minefield installation. This creates additional noise, obscuring the planted ordnance and increases the rate of false alarms, slowing down the process drastically. One of the promising approaches to landmine detection is electro-optical sensors. Modern mine detection methods focus on increasing the detection radius and expanding the types of mines they can detect. Each method is suitable for detection in specific conditions, depending on the type of mine casing, explosives, and soil. However, universal detection is extremely hard to achieve with a reasonable level of precision. Among electromagnetic sensors, hyperspectral sensors are most suitable for solving the problem of mine detection, since they have a high number of channels that allows detecting mines, while providing a good balance between dimensionality, the amount of useful information, and the speed of intelligence system. However, such sensors are extremely expensive, hard to acquire and maintain. Out of hundreds of spectral bands they capture, only few carry useful information for landmine detection. One such narrow band is infrared band, which captures the radiation of heat by different objects. Under right conditions, this narrow band has enough information to accurately identify a landmine location. Now, there are also challenges to using thermal imagery for landmine detection. Noise and blur is a major consideration as we uncovered during our experiments. The information available in thermal band is rich but also sparse. As such, noise and blur have much higher effect on classification and segmentation or object detection tasks compared to other sensor types. There are also dataset limitations. Collecting and annotating thermal data is hard and time consuming. To extract useful information from the image, strong thermal gradient is necessary, otherwise a high rate of false positives can be expected due to weak signal. Lastly, there's spatial spectral coupling. Spectral features are key for material recognition, but special features such as texture and context are also important for accurate classification. Considering the sparsity of spectral domain, accurate object classification might be challenging depending on conditions. A quick note on sensor fusion. Some of methods' limitations can be overcome with sensor fusion techniques that would allow to add extra channels to source data. In this work, we have considered the possibility of adding a visible part of the spectrum to expand the available information. However, after some experimentation, reached the conclusion that it's best to consider such data independently. Key problems that we have encountered are first and foremost sensor desynchronization, which makes it quite hard to align to data sources. Then there's different resolution and capture frequency of sensors themselves. Also, there's awkward matching and inability to mount two sensors at the same time on the mobile platform of our choice. It's a bigger problem for bigger sensors. In this case, we were able to do it, but in some cases, it's challenging. And then there's different feature domains, which makes training the neural network a little bit harder. The consider framework is developed in two possible configurations. The first one being inference in a batch mode, and then there's inference in real-time mode. In a batch mode, the whole area first scanned with a UAV with sensor attached, and thermal orthomosaic is generated. It is then sliced into smaller pieces, which are fed through pre-processing pipeline and into CNN. It works well for large-scale demanding operations and reconnaissance, but is not as useful in the actual landmine removal process. On the other hand, real-time scenario is much more useful in a real-time process as it can aid operators on the ground as they move through the minefield. However, it also has some challenges. First of all, we have to work with a small slice of the thermal footage. which means that certain pre-processing techniques are much harder when compared to processing the whole orthomosaic at once. Uh, Another thing to note is that it imposes certain performance limitations on the system, which limits the architectures of neural networks and preprocessing steps we can use to hit the near real-time requirements. Preprocessing pipeline is somewhat neglected by other studies that use similar approaches, but in this case, since we need to adhere to real-time limitations, we have looked into building a robust preprocessing pipelines that would aid us with feature extraction partially and allow us to use simpler neural network architecture. The preprocessing pipeline consists of three steps. The first one being normalization. During this step, spectral image is normalized and filtered. First, all data is normalized channel by channel using min-max normalization. In this case, we have only one channel, but we also use two types of normalization. The first one being global, where each pixel is normalized according to the whole training batch, and the other being local, where each pixel is normalized in relation to other patches in the image to make sure that image covers the whole uh, domain possible. The second step is texture extraction. We use local binary patterns for histogram extraction, and this is a special filtering method that is used to extract special features, especially textures, with significantly increased the classification accuracy. In our case, its primary role is to remove smaller chaff and noise from the image, because extracting texture itself from the landmine is extremely tricky. The last step is filtering. So after the histogram is created, an additional filtering stage is performed. In this stage, we use a morphological filtering to remove noise and speckles from the image. A morphological filter allows to filter out noise and insignificant objects from the textures. Usually it's bigger objects like small rocks, for example. And this process is based on tools from a set theory for analyzing and processing the spectral features of image based on set theory. Now, the most important part of the pipeline is feature extraction and classification. We use an approach based on fast regional CNN for object detection. It consists of several types of layers, the key being convolutional layer, which is a basic building block of a CNN, where the convolution operation occurs. Filters, aka kernels, slide over the entire image, calculating the dot product between the filter and a portion of the input image. Then pooling layers are used to reduce the dimensionality of feature map and aggregate it into the actual feature map itself. We also have batch norm layers to normalize feature maps, dropout layers to prevent overtraining, and fully connected layers, which are used towards the end of the network for classification and bounding box extraction. The first operation that is performed on the image itself is region of interest projection, which generates k bounding box anchors from the image, which are then passed through convolutional paths and fed into fully connected layers. In the end, fully connected layers diverge into two separate passes, with one leading to a sigma-based classification framework, since we solve the problem of binary classification, whether the landmine present or not. And then there is bounding box regressor, which identifies the bounding box of the landmine. To test and evaluate the proposed system, an experiment was conducted to collect data, train, and evaluate the proposed system. Data was collected using a DJI ZH-20T thermal camera attached to a Mavic Phantom T4 quadcopter. The mines were installed on the surface and also buried in the ground to a shallow depth of up to 10 centimeters. The study used two types of mines, the anti-tank and anti-personnel mines. Both types had a metal casing in this case. The flight was carried out at low altitude first, with 5 to 6 meters being the average altitude of the flight, and then medium altitude on 10 to 11 meters altitude. The integrity of grass cover was damaged only in the places where the mines were installed, but otherwise the cover remained intact. Data were collected in clear, warm weather to minimize noise and maximize image quality. The temperature was shifting throughout the day, which ensured high quality thermal gradient in the collected dataset. The neural network was trained in batches of 16 images. The sample size is bolstered by applying weak augmentations that consist of rotation, stretching, and other augmentations from rand augment. The preprocessing stage was performed for each batch separately to increase the generalization ability of the neural network. Adam learning algorithm with a decaying learning rate from 1000 to 1/10,000 is used during the training of the neural network. The experiment results can be seen on the screen. We were able to achieve reasonable precision of zero point 0.9. Our recall is perfect at 10. Rand index or overall accuracy is 0.98, being a little bit skewed by false positives that were detected in several images, and intersection over union metric is reasonably high at 0.96. It's worth noting that in the case of intersection over union, the problem was that bounding boxes were a little bit bigger than anticipated, so they were covering not just the landmine but also patches of grass around it. But in the context of this problem, it's a minor concern as the whole landmine was covered with the bounding box. Overall, the algorithm performed well, detecting both landmines installed over the ground and under the ground with high reliability. However, it should be noted that even on a small number of samples and with a large number of training iterations, the network has somewhat modest precision. Future research focuses around two factors: improving learning and stability and improving computational performance. Improving generalization ability through a variety of data sets, which allows to apply it either in zero-shot or lightweight fine-tuning scenarios, is important for the method being applied in practice, and improving models object detection through more complex object detection methods like masking, RCNN, or YOLO could improve precision that we struggled with about. Also, improving computational performance is another consideration. Simplifying network structure and removing unnecessary layers via convolutional architecture simplification is considered, and further improvements can be achieved through knowledge distillation to decrease number of parameters in the network. The proposed method detects landmines with high recall and adequate precision. The proposed method is able to leverage thermal imagery captured by drone in automatic flyby mode, which allows for coverage of large areas of polluted land quickly, and the method is lightweight and with some minor modifications can be used in real-time scenario to assist in landmine detections. That's the conclusion of this research, and thank you for attention.